Hi everyone, in this video I'll be proving the first isomorphism theorem. Before I start, I have a few important results that I'd like to share. The first one is the definition of a homomorphism. So a homomorphism is a map from the group G to the group H, and if we say X and Y are in group G, then a homomorphism is a map that preserves the group action. Secondly, we have these identities here, and I'll be using them. And thirdly, we have this third property, which says that the identity in G is mapped to the identity in H. And we have this second one, which says that the homomorphism maps the inverse of G to the inverse of theta G. Now we can prove the first isomorphism theorem. So the first isomorphism theorem tells us so we have three important results, and they are, the first one is the kernel of theta is a normal subgroup of G, and we define G by theta as a we define theta as a homomorphism from G to H. And the second important result is that the image of theta is a subgroup of H. And the third important result is that the quotient group G over the kernel of theta is isomorphic to the image of theta. So I'll be proving these one by one, and let's prove the first one. So the kernel of theta is a normal subgroup of G. We'll be proving that the kernel of theta is a subgroup first, and then we'll prove it's a normal subgroup. So closure. I'll be proving the group axioms one by one. So let's say x and y sit in the kernel of theta. Therefore, by definition, we have theta xy is equal to theta x, theta y. And by the definition of the kernel, these two are equal to EH, the identity in H, which is equal to the identity in H. And by definition, theta xy is equal to the identity in H, and that's the definition of the kernel. Hence, xy sits in the kernel of theta. Now we are going to prove the identity. And this was one of the results I showed earlier. So the identity in G is mapped to the identity in H. Therefore, the identity in G sits inside the kernel. Now I'll be proving the inverses. Let's assume that x sits inside the kernel of theta. Therefore, we have theta x is equal to EH. And now let's consider theta x inverse, which is equal to theta EG, which is equal to the identity in H. And we also know that this is equal to theta x minus 1, and this is equal to EH. I know that theta x is equal to EH, therefore we have theta x minus 1. Therefore we have theta x minus 1 is equal to EH, and by definition x minus 1 sits inside the kernel of theta. And I'm going to write this here. We also have the associativity, and it is inherited because the kernel of theta, every element in the kernel of theta by definition has to be inside G. Therefore, the associativity is inherited. Now we have to prove that it's a normal subgroup. prove kernel of theta is normal. Now let's assume x is inside the kernel of theta, hence consider g inverse x g. This is equal to theta is a homomorphism again in this case. This is equal to theta g inverse theta x theta g, and by definition theta x is equal to EH. And I'm going to skip a step here and then write theta g inverse by the important results I showed earlier, and theta g, and this is equal to EH. Therefore, because this thing is mapped to the identity in H, we know this sits inside the kernel of theta. Therefore, and this works for all g in G. Therefore, kernel of theta is a normal subgroup of G. So that was the first result, the first important result that's given by the first isomorphism theorem. Now we are going to move on to the second one, and that one says the image of theta is a subgroup of H. So again, I'll be proving the group axioms one by one. So let's say y and y1, so this is closure. Let's say y and y1 sit inside the image of theta, and let y is equal to theta x, y1 is equal to theta x1, where x and x1 sit inside G, and obviously theta is a homomorphism from G to H. Therefore, y1 is equal to theta x1 is equal to theta x1, and therefore because this sits inside G by closure, because x and x1 are inside G, therefore by closure x1 sits inside G, therefore it is the image of this whole thing is the image of something, therefore y1 sits inside the image of theta. So this was closure. Now I'm going to prove the identity. Theta EG is equal to EH, therefore EH sits inside the image of theta. Now I'm going to prove the inverses. So that's in case you couldn't see the bottom bit. Now I'm going to prove the inverses. So let y be an element in the image of theta, and let y is equal to theta x, where x is equal to x is inside G. Therefore, by closure, we know that x inverse is also inside G. Therefore, we know the theta of x inverse sits inside the image of theta, and by using the important results I showed you, this is equal to this, and this sits inside the image of theta, and this is equal to y inverse, and it sits inside the image of theta. Therefore, inverses work. And associativity again is inherited, because every single element in the image of theta has to be inside H by definition. So we have proven the image of theta is a subgroup of H. Now moving on to the third important result, that's to say the quotient group of G by K is isomorphic to the image of theta. So in this case, to prove that this is isomorphic to this, we need to set up an isomorphism between them. So let's define phi, an isomorphism from G by K to the image of theta. Let's say phi maps gk to theta g, which means phi gk is equal to theta g. So to prove that it's an isomorphism, we have to prove 4 things. So first we have to prove that phi is well defined. Secondly, we have to prove it is a homomorphism. Thirdly, we have to prove it is a bijection to prove that it's an isomorphism. And we prove that it's a bijection by proving that it is injective and surjective. Okay. So let's prove that phi is well defined first. Let me show this piece of paper again, in case you couldn't see the bottom bit. Okay, so let's prove that phi is well defined first. So let gk and hk be the same thing, and let's consider now we have to consider wait a second. Yes, yeah, if they are the same thing, we know h minus 1g sits inside k, and I just used an important result here. So if AH is equal to BH, then we have B minus 1A sits inside H. This is just something you need to know. Yeah, so we have this. And because H minus 1G sits inside K, which is the kernel, by definition we have theta H inverse G is equal to EH. And we have theta H inverse theta G is equal to EH. Theta G is equal to theta H inverse and theta G is equal to theta H. And therefore phi gk is equal to phi hk. Therefore, if they are the same thing, they map to the same thing, which means the notation doesn't make a difference. And next we have to prove that phi is a homomorphism. Phi is a homomorphism. So let's consider phi gk hk. So in this case we are going to use the first result of the first isomorphism theorem. We have proven that k is normal, therefore kh is equal to hk. Therefore this could be written as ghk k, which we could just write as a single k. In fact, I don't even know if this is correct. Yeah, so, and this is equal to, by definition, theta gh, and because theta is a homomorphism, we have theta g theta h, and this is equal to phi gk phi hk. Hence we have shown that phi is a homomorphism. Now we have to show that phi is surjective. Yeah, let me just show the bottom bit of the last one. Yeah. Now we have to show phi is surjective. So in the first place we defined phi as a map from g by k to the image of theta, and we said gk was mapped to theta g. So therefore by definition for every theta g inside the image, there exists gk such that the phi of gk is equal to theta g by definition. Therefore, every single theta g is hit, therefore phi is surjective. Now we have to show it is injective. And we show that it's injective by letting that phi gk is equal to phi hk, and we have theta g is equal to theta h, and rearranging this gives theta h minus 1 g is equal to eh. Just to be clear, theta g, theta h inverse theta g is equal to eh, and using the important results I showed in the beginning, theta h inverse theta g is equal to eh, and because theta is a homomorphism, we have theta h inverse g is equal to eh, and this is what we have here. If theta h inverse g is mapped to eh, by definition, h inverse g sits inside the kernel of theta. Therefore, h minus 1g sits inside k, and by what I have shown previously, which is the result that h minus 1g, if h minus 1g is inside k, then hk is equal to gk. Therefore, if they map to the same thing, they must be the same thing, therefore phi is injective. So as a result, what we have done is we have proven the first isomorphism theorem using our important results. And to summarize, the first isomorphism theorem tells us that the kernel of theta is normal in G, and the image of theta is a subgroup of H, and the quotient group generated by K, the quotient group of G generated by K is isomorphic to the image of theta. Thanks a lot for watching. I hope this was helpful, and let me know if you have any questions in the comments below.